Topic today is about differential equations. We all know that a differential equation, it is an equation containing at least one derivative or differentials. And I know that all of you know what a derivative or differential is because you already tackled it during your differential calculus. In this topic, we are going to identify what would be the order or the degree of a differential equation. First is the order of the differential equation. To identify what is the order of this differential equation, take note that it is the order of the highest ordered derivative in the equation. For example, we have a differential equation here. So d squared y over dx squared plus the cube of dy over dx minus 2y equals 0. And then we have also here, so y, this equation is under the second order, and why this, our second equation, is under the first order. Because our first equation just focus on the highest derivative, and we all know that this is in the second derivative. Okay, so what is the degree? Its order is the highest order derivative in the equation. So since it is in the second derivative, so we can say that this is in second order. So our second equation, since this is only a first derivative, we could say that this is in the first order. Okay, so now what about the degree of a differential equation? Actually, it is the degree or the degree of the highest power of the highest order derivative in the equation. So the same concept, just focus on the highest derivative and then the degree of the highest derivative. So here, last time, we all know that this equation is under the second order. But what is the degree? This is second order but first degree, because the degree of the highest derivative is just 1. Well, our second equation, it is in the second degree, so this is an error. So this is a fourth order but a third degree, so that is the degree of the differential equation. So now, before we introduce to the main topics of the differential equations, we must first know what are the types of solutions of a differential equation. The first one is a general solution. It is a solution that contains at least one or more arbitrary constant. Just for example, here in our equation, y is equals to c sub 1 e raised to 2x plus c sub 2x. Our arbitrary constant here is the c1 and our c2. And this equation is our general solution. Take note, it contains one or more arbitrary constant. The second one is the particular solution. It is a solution that do not contains any arbitrary constant. So from this equation, there are neither C1 nor C sub 2 that you had seen because it has no arbitrary constants. The first topic that we are going to tackle in a differential equation is the elimination of arbitrary constants. From this topic, from the title itself, the elimination of arbitrary constant, our only goal here from the given differential equation, our only goal here is just to eliminate all the arbitrary constants. And we all know, in order to eliminate or to cancel or to eliminate the constants in calculus is differentiation, or we're going to derive to eliminate all the arbitrary constant. Okay, so here our first example. Take note, if you have only one arbitrary constant, just derive once. If you have two arbitrary constant, you must derive it twice. So it means that the number of arbitrary constants you have, that is also the number of differentiation that you will be having to cancel or to eliminate all the arbitrary constants. So here our first equation, our first example is x cubed minus 3x squared y equals c. And we all know that our c here is the arbitrary constant. And we have only one arbitrary constant. So we are going to differentiate this equation once. Solution. So x cubed, it's, if we're going to derive this one, we have 3x squared minus, and now we all know that x squared and y, we're going to apply the product rule. So this is vdu plus udv. So x squared, the derivative of y with respect to x, plus y, the derivative of x squared with respect to x, equals to 0. And then copy, and then the derivative, so this is dy over dx, plus the derivative of x squared is 2x. So we have, so 3x squared minus 3x squared dy dx, so negative 3 times, so this is 3 times 2 is 6, so xy, so the sign is negative, so this is negative xy equals to 0. So here, so if we're going to divide or to multiply all terms by 1 over 3, or we are going to simplify this equation, we have x, okay? Or I mean, if we divide it in 1 over, multiply in 1 over 3x, so we have x minus, so x dy dx minus, so 2y equals 0. Okay, so this is it, x minus x dy dx minus 2y equals 0. So if we're going to simplify, so we put this into the right side and then cross multiply. So overall, we have x minus 2y dx equals x dy. Just cross multiply this equation. So this equation is now the final answer. The arbitrary constant here was already eliminated. Our second problem is x squared y equals 1 plus cx. Still, our goal is to eliminate the arbitrary constant. So here, we have only one arbitrary constant. So we are going to differentiate this only once. Okay? So x squared y, again, minus 1 equals cx. So I think it's in your idea or how are you going to simplify this, but for me, just separate the arbitrary constant so that you can be able to differentiate freely the other variables. So again, we are differentiating this equation in terms of x. Okay, so I have here, so I divided all terms by x. So here it is. Okay, so if we're going to divide, so x squared y divided by x is xy. 1 divided by x is 1 over x, equals 0, c. So this is already differentiable, just differentiated. So this is in the product rule. So x dy dx plus y dx dx, so y times 1 or y. And here it is, so this is negative 1 over 1x, so or it is a 1 over a 1x raised to negative 1, so negative 1 times negative is positive, and the negative 1 minus negative 1 is negative 2, so it is a 1 over x squared equals to 0. Yeah. Okay, so here it is, so just transpose. all terms except for the term that have the dy dx. Okay, so here it is. So x dy over dx equals negative y minus 1 over x squared. And then we're going to here, so just get the LCD. So we have here the LCD of x squared. And then our numerator for the negative y, we have negative x squared y minus 1. So we can cross multiply these two terms. So we have now dy dx equals negative x squared y minus 1 over x cubed. So the x here, if we're going to multiply by 1 over x, so we have x cubed. Now our turn is to cross multiply. So x cubed times dy, we have x cubed dy, and then equals, so here it is, so dx times here negative x squared y minus y. And this is already our final answer. The arbitrary constant, which is the c, was already eliminated using just a simple derivation. So our third example is our equation is y equals c sub 1 plus c sub 2 e raised to negative 4x. So again, our goal is to eliminate all the arbitrary constant. And we all know that in this equation we have two arbitrary constants. So our goal here is to differentiate the equation twice to suffice, or to eliminate the two arbitrary constants. So here it is. So our first derivative will be negative 4 c sub 2 e raised to negative 4x. So how? We all know that this is a constant, so if we're going to derive this one, this will be 0. And then the e raised to negative 4, we have the u here, so negative 4 c sub 2 e raised to negative 4x. And then we are going to differentiate again. So the negative 4 times negative 4 will be positive 16. And then copy the c sub 2, so I forgot to put the c sub 2 here, e raised to negative 4x. Okay, now how are we going to eliminate the arbitrary constant? It's simple. Using the matrix technique, we will have, so okay, so just input here, so y, here it is, so this is the matrix technique, so y prime, okay, copy y double prime, and then the c sub 1, what will be the coefficient of the c sub 1? Here is 1. Our second equation, I mean the first derivative, we have we have no c sub 1, so we will be putting 0. And the same with the second derivative, that this is 0. Okay, again, the first equation for the coefficient of the c sub 2e raised to negative 4x, so just observe that you are going to neglect or to omit the terms that are alike in these three equations. So we all know that the similarities of these three equations, so we have c sub 2 e raised to negative 4x. So here it is again, same. So we have c sub 2 here. So if we're going to get the coefficients for this term, I mean for this one, c sub 2 e raised to negative 4x, since all the equations have c sub 2 e raised to negative 4x. So the coefficient of our first equation is 1. So here it is 1. And then the second equation is negative 4. And the last equation is positive 16. Okay? So in this technique, we're going to copy the second column, I mean the two columns, the first two columns, so here, so y, so copy here, so just copy. And then first is to multiply up to down. So y times 0 times 16. So here it is. So y, this is 0. So 1 times negative 4 times y double prime, this is negative 4 y double prime. Then 1 times y prime times 0, this is 0. So okay na. So this is it. So minus, always in minus. So upper to lower minus lower to upper. So y double prime times 0 times 1 is 0. 0 times negative 4 times y is 0. But then 16 times y prime times 1 is positive 16. Since lower to upper, so this is negative 16 y prime equals 0. So I think there are some methods to eliminate the c sub 2 or the arbitrary constant. Just use the elimination or substitution, so you can use other technique. But then, so this is already our final answer. So if we're going to divide all terms by 4, so we have y double prime plus 4y prime equals 0. So this is already our final answer. Y equals c sub 1 e raised to x plus c sub 2 e raised to negative x. We all know that we have two arbitrary constants. That is why we're going to derive these equations into, twice. So the first derivative, this will be the first derivative of y is y prime equals, so c sub 1 e raised to x, and then we have a negative 1 here, so negative 1 c sub 1 e raised to negative x. Then the second derivative, so copy, so the second derivative, so this is the same, c sub 1 e raised to x plus c sub 2 e raised to negative x. Okay, so again, using the matrix technique, so we have here, so okay, copy y prime, y double prime, so just copy here. So for the coefficient, for the arbitrary constant c sub 1, what are the like terms? The like terms here is c sub 1 e raised to x. So all the equations, we have first equation, second equation, and the third equation. All those equations have c sub 1 e raised to x. So we are just going to get the coefficients of the equations that are similar to this three. So we have 1 for the first equation. So just for the first term, for this is sub 1 arbitrary constant. So for the second equation, for the first derivative, we have also 1 coefficient, then 1 coefficient here. Okay, and then for our last term, for the term involving c sub 2, so we all know that all these equations, these three equations have, they are similar in terms of c sub 2 e raised to negative x. So that is why we are going to omit this one and just copy the coefficients. So for our first equation, the coefficients here is 1. For the second equation is negative 1. So here it is, negative 1. For the last equation is positive 1. And then again, for this technique, I'm just going to copy the first two column here and then multiply from up to lower. So all here, and then minus lower to upper. So here, like that. Okay, so first, so y times 1 times 1, this will be y. Second, 1 times negative 1 times positive y prime, this will be negative y prime. 1 times y prime times 1, this will be positive y prime. Minus from lower to upper. So y double prime times 1 is, this will be y double prime. 1 times negative 1 times y, this will be negative y. 1 plus y prime times 1, this will be positive y prime equals 0. So just simplify. So here it is. So y minus y double prime plus y prime minus y double prime plus y minus y prime equals to 0. So I think here this will be cancelled out. Okay, so we have here. Okay, so we have negative 2y plus positive 2y double prime. So if you're going to simplify this equation, we have y double prime minus y equals 0, and this is already our final answer.